Today we're going to be looking at this problem. Every day, a kindergarten class chooses randomly one of the 50 state flags to hang on the wall, without regard to previous choices. We are interested in the flags that are chosen on Monday, Tuesday, and Wednesday of next week. Part A states to describe the sample space omega and probability measure p to model this experiment. Part B asks for the probability that the class hangs Wisconsin's flag on Monday, Michigan's flag on Tuesday, and California's flag on Wednesday. And then Part C asks, what is the probability that Wisconsin's flag will be hung at least 2 of the 3 days? All right, so let's start with Part A. So recall that the sample space is the set of possible outcomes. So in this case, our outcomes are precisely a triplet of flags, one for the flag which gets hung on Monday, one for the flag that gets hung on Tuesday, and one for the flag that gets hung on Wednesday. Now, the probability measure is going to associate, we're not given any information besides the fact that these flags are chosen randomly. So our probability is just going to associate an equal 1/50 probability of choosing each state flag. So that means that each event is going to get assigned a probability of 1/50 cubed, as we will see. So let me go ahead and fill in the answer to Part A. So as we stated, omega is going to be equal to, if I look at the set of 50 state flags, so Alaska, Alabama, ... and then all the way maybe to Utah. I apologize if I missed your state. Yeah, actually, it'd be funny is if you live in the U.S., comment what your state flag is, or if you don't live in the U.S., then maybe leave in the comments what part of the world you live in. So anyways, this set will be a set of size 50, and it's going to enumerate all the possible states whose flags we're considering, and then I'm going to raise this set to the power 3. So remember, if I raise a set to a power, this is with respect to the Cartesian product. So raising to the power 3 essentially means that our elements are triplets, like x, y, z. So for example, I could have a triplet Utah, Wyoming, or let's say, yeah, Wyoming, and maybe Nevada. Okay, so these triplets are the typical member of this set to the third power. So each coordinate in the triplet, or each entry in the triplet, represents an element of this set. And then when I raise the set to the third power, I'm basically encoding these triplets in the following manner. So this is exactly the information that we want to encode. And the first element of the triplet is going to be the flag that's chosen on Monday. The second element of the triplet is going to be the flag that's chosen on Tuesday. And the third element of our triplet is going to be the flag that is chosen on Wednesday. Okay? And now, so to assign my probability measure, P, recall that the probability measure is a function from the power set of omega to the real numbers, which satisfies 3 specific axioms. And if you want to review those axioms, go back to a few videos ago, exercise 1.1, where those axioms were stated explicitly. But just a brief recall, a probability measure has to keep its values between 0 and 1. It is a function from the set of subsets of omega into the real numbers, and it assigns the total space a probability of 1, the empty set a probability of 0, and it satisfies a summation property where the probability of a disjoint union of events is the sum of the probabilities of each of those events. Okay? So in this case, our probability measure is going to be uniform, and it's going to assign a certain tuplet, let's say x, y, z, is going to be equal to, well, I know the probability of the probability of choosing flag x on Monday should be 1 over 50. And then the probability of choosing flag y on Tuesday should be 1 over 50. And the same probability for choosing z on Wednesday. So the probability that I actually made all three of those choices is simply the product, 1 over 50 times 1 over 50 times 1 over 50, which is 1 over 50 cubed. Okay? And let me just write it like this. So, okay, so now the reason why we can split this into a product of 1 over 50s is essentially because of this statement here that that we're choosing our flags without regard to previous choices. So we can choose the same flag twice. We have no memory of our previous day, the previous like if it's Tuesday, we have no memory of what we chose on Monday. So all flags are equally likely to be chosen on Tuesday, which means that that each of these events is somehow independent, and so the probabilities will multiply in this fashion. Now, also recall that by specifying the probability of every possible outcome, I fully specify the probability measure on my sample space because of the axioms of probability measures. If I look at any event, which is any subset of omega, well, since omega is a finite set, every subset is going to be a finite set, and those finite sets are going to consist of elements of this form, and by assigning a probability to each of these elements, then we automatically ensure that the probability of any subset of the set is simply the sum of the probability of all the elements. Okay, so in math notation, if A is, let's say, some union of elements xi, yi, zi, where I goes from 1 to n, then the probability that A occurs is simply given by the sum of the probabilities of each of these yi, zi's occurring. Okay. All right, so I'm basically going in circles, overly complicating this, but really what I wanted to say was that the probability of a single outcome is 1 over 50 cubed, and this is enough to specify the probability of any event happening. Okay, so now let's move on to part B. What is the probability that the class hangs Wisconsin's flag on Monday, Michigan's flag on Tuesday, and California's flag on Wednesday? Okay, so to answer this question, we're just going to recognize that this is just a single outcome. This is just a single Wisconsin, Michigan, and California. So for part B, we're just looking at the probability of Wisconsin, Michigan, and California. Well, this is just a single outcome. We assigned this probability already, and we said that it's no matter what these three elements are, this is always 1 over 50 cubed. Okay? All right, now, so that's immediately done. Now, part C is a little bit more interesting. Part C asks, what is the probability that Wisconsin's flag will be hung at least 2 of the 3 days? Okay? So now we have to think a little bit about this. So what we need to determine is we have this event. The event is that Wisconsin's flag is hung at least 2 of the 3 days. Okay? And we need to determine essentially the size of this, the amount of possible outcomes, which fall into this category, okay? So, right, so there's two possibilities, okay? So case one is that we have Wisconsin is hung on all 3 of the days. And the probability of this event happening is, as we already determined, exactly 1 over 50 cubed. So the probability of any individual outcome happening. Okay? Now, let's look at the other possibility, which is that Wisconsin's flag is hung on 2 of the 3 days, okay? So case 2 is going to be if Wisconsin is hung on 2 of the 3 days, and so this is going to look like Wisconsin being hung on Monday and Tuesday, and then doesn't matter what the third flag is. We could also have Wisconsin hung on Monday and Wednesday, and we also might have Wisconsin hung on Tuesday and Wednesday. Okay, so these are subcases of case 2. So let me just state case 1 is all 3 days, and case 2 is exactly 2 days. Wonderful. Now we need to, now that we've kind of broken this down into cases, let's analyze this specific case. So if Wisconsin was hung on Monday and Tuesday, what's the probability of this happening? Okay, so the probability of this happening, okay, and if I should really kind of be careful here and really denote the set, really use the proper notation, which is that let's denote the set A to be the set of all x, y, and z in omega such that x is equal to Wisconsin and y is equal to Wisconsin. Okay, so this is precisely the event that Wisconsin gets hung on Monday and Tuesday, and notice that this event is a subset of omega, which consists of multiple possible outcomes. Namely, there's an outcome for each possible choice of z. Okay, and so the cardinality of A. Well, the cardinality of A is exactly 50 because there's 50 possible choices for the flag on the third day. Okay. But I'm a little bit off here because, in fact, the cardinality of A is not 50. It's actually 49. The reason is that we've specified in this case that this event must occur exactly 2 days. So we must hang the Wisconsin flag for exactly 2 days. We've already taken care of the case where we hung the Wisconsin flag for all 3 days. So in this case, I'm not allowed to hang the Wisconsin flag again in my set A. So I should add the condition that z is not equal to Wisconsin. Okay? Wonderful. So now this is my set A and it has cardinality 49. And by symmetry, all 3 of these, let's say this is case 1, case 2, and case 3, all 3 of these cases represent events whose cardinality is 49. So let's call this set A1, and then the corresponding sets for 2 and 3 will be called A2 and A3 respectively. And then the probability that Wisconsin's flag is hung on at least 2 of the 3 days is precisely the probability that either A1 happens or A2 happens or A3 happens, so one of these three cases, or we hang Wisconsin on all 3 days. And this is a singleton event. Okay? And now, by the axioms of probability that I mentioned and perhaps stumbled over earlier, we actually, since this is a probability measure, it's going to sum over disjoint unions. Now recall that a disjoint union means that these sets or these events cannot have any elements in common. And that's the key, is that we've actually made sure that these don't have anything in common because we've specified that, for example, all 3 Wisconsins cannot occur in A1, A2, and A3. So in particular, if we look at A2 and A1, okay, then there are no outcomes in A2 which also belong to A1, because if my outcome belongs to A2, then I've chosen Wisconsin on Monday and Wednesday. But if I've chosen Wisconsin on Wednesday, then I cannot belong to A1, because we've stipulated in A1 that Wisconsin cannot be chose on Wednesday. Okay, so these are actually disjoint events. And then finally, we've included the singleton event where we chose Wisconsin all 3 of the days. And because these are disjoint events, I can sum over them. And so I get the probability of A1 plus the probability of A2 plus the probability of A3 plus the probability of this singleton. Okay, and then the probabilities of these events, well, we know that each outcome, as we specified earlier, each possible outcome has a probability of 1 over 50 cubed. And so the probability of this event occurring is simply its cardinality divided by 50 cubed. Now, recall that the cardinality of the set is simply how many outcomes or how many elements belong to that set. Okay, so we're going to end up with the cardinality of A1 plus the cardinality of A2 plus the cardinality of A3 plus 1 all over 50 cubed. We know that each of these cardinalities are 49, and so I'm going to end up with 3 times 49 plus 1 divided by 50 cubed. All right, and that should do it. Thank you.